Hello friends, good morning. I welcome you all for today's session. In today's session, we'll be looking at a derivation. It's called a shape function of three-noded bar element in terms of natural coordinates. Right, so let me start with the derivation part. I have considered an element and I have divided the element into three nodes, node number 1, node number 2 and node number 3. And since it is in natural coordinates, we know natural coordinate is zeta, whose maximum value is 1 and minimum value is -1. So at node 1 I have taken it as -1, at node 2 I have taken it as +1, whereas the intermediate node I have taken it as 0. Right, I hope things are clear. Next, above element has 3 degrees of freedom, therefore the polynomial with 3 generalized coordinates should be selected. Now 3 degrees of freedom, what I mean is node 1, node 2 and node 3, each of this node can get displaced or can move in a direction. So there are 3 degrees of freedom, right? Now once if we are done with this, I am going to assume a function u is equal to alpha 1 plus alpha 2 zeta plus alpha 3 zeta square. Since it is a quadratic element, I am going to assume this. One more reason is since it is having 3 degrees of freedom. Right, in the previous case it was a linear element, so we had limited ourselves to alpha 1 plus alpha 2 zeta because it was a linear element. Since it is a quadratic element, there is one more term which we need to consider, that is alpha 3 zeta square. Right, so once if you consider this, the next thing is writing above equation in matrix form we get. Right, so this equation 1 I am going to write it in matrix form. So I can write it as U matrix is equal to, told you it is very important, so it is alpha 1 alpha 2 alpha 3. Now we need to jot down the coefficients of alpha 1 alpha 2 alpha 3 in the above equation. So alpha 1 coefficient was 1, alpha 2 coefficient is zeta, alpha 3 coefficient is zeta square. Right, so if you multiply this 1 into alpha 1 plus alpha 2 into zeta plus alpha 3 into zeta square, you should get back the equation. Right, fine. So this you can take it as equation number 2. Now at node 1 zeta will be -1. So above equation becomes, therefore this equation becomes u1 is equal to alpha 1 minus alpha 2 plus alpha 3. Right, this you take it as equation number 3. How I got this? In equation number 1 I have substituted the value of zeta, so I have got one equation that I have taken it as equation number 3. Now similarly at node number 2 zeta is equal to +1. Right, at node number 2 zeta is equal to +1. Therefore this equation becomes u2 is equal to alpha 1 plus alpha 2 plus alpha 3. This you take it as equation 4. At last at node number 3 zeta value is 0, so this equation becomes u is equal to, u3 is equal to alpha 1, the rest two elements will become 0, so this is equation number 5. So next thing, expressing equations 3, 4 and phi in matrix form. Right, we need to express equation 3, 4 and 5 in matrix form. So that can be written as u1, u2, u3 right. So we are having alpha 1, alpha 2, alpha 3. Now if you want to express this equation in the form of matrix, Joule down alpha 1, alpha 2, alpha 3, here horizontally you need to write the coefficients of alpha 1, alpha 2, alpha 3. So coefficient of alpha 1 was 1, coefficient of alpha 2 is -1, coefficient of alpha 3 is +1. That is how you write it. Similarly for the second one, all the coefficients are positive, so it becomes 1, 1 and 1. In the third case, there is only one coefficient, that is for alpha 1 we are having 1, alpha 2, alpha 3 are missing, so you take it as 0. Right, now I'll take this as U matrix, I'll take this as A matrix, and I'll take this as alpha matrix. Right, now this you take it as equation number 6. Therefore alpha is equal to U into A inverse. This you take it as equation number 7. Right, what I have done, I have assumed this as U equation, A equation, or you can take it as A matrix, alpha matrix. I am in need of alpha matrix, so I'll keep it on the right side. If you take A to the left side, it is U by A. Then if you take A to the numerator, it becomes A inverse. So now my task is to find out inverse. So you know how to find out inverse. In the previous video also I have shown you. A inverse is given by adjoint of A divided by determinant of A. Right, also adjoint of A is transpose of matrix of cofactors. Right, so these are very important things. Next, let me find out the inverse part. So to find out inverse, first let me write what is the A matrix. So A matrix is 1, -1, 1, 111, 1, 0 and 0. Right, so this is the A matrix. I need to find the inverse of this. Now first I'll be finding cofactors, so I'll just write it as cofactors. Now first A11, you know how to find it. It is -1 raised to 1 plus 1. Why 1 plus 1? I told you in the previous video, if it is first row first element, you should take it as 1 plus 1. Now you leave the first row and first column. If you are going to leave the first row and first column, you will be having only these two things. Then you need to find the determinant of this. How you find the determinant? In this case it is 0 minus 0. Right? 0 minus 0. So you will be getting it as 0. Now A12. So it is -1 raised to 1 plus 2. So first row and second column. First row and second column. Right? First row and second column. So only 4 elements are remaining. 1 1 1 0. You need to find the determinant of that. So it comes out to be 1 minus 0. 1 minus 0. So it is 1 and -1 raised to 1 plus 2 is minus 1, so outcome is minus 1. Similarly A13, so it is given by minus 1 raised to 1 plus 3. So it is first row third column, first row third column. You need to skip this particular part, right? So remaining thing will be 1 1 1 0. Once again, if you find the determinant, it is 1 minus 0. So if you write it as 1 minus 0, check out minus 1 raised to even number is positive, so you'll be getting 1, right? Similarly, I need to find out A21, where it is minus 1 raised to 2 plus 1. Now it is second row and first column, right? Second row you need to remove and first column you need to remove. You'll be having 4 elements, 1 2 3 and 4, which are remaining. Now if you take the determinant of this, you'll be getting 0 minus 0, right? So the resultant will be 0. So for A22 it is minus 1 raised to 2 plus 2. Strike out the second row and second column, and for remaining elements you find out the determinant. So this I need to remove, this I need to remove. For remaining elements, 1 into 1 is 1, 1 minus 0, 1 minus 0. So A22 comes out to be 1, and A23 minus 1 raised to 2 plus 3. So now I need to remove the second row and third column. So now it is 1 into minus 1 is minus 1, second row and third column. So 1 into minus 1 is minus 1 minus 0. So just check out how much it is. A23 will be plus 1, because this minus into this minus it will be. Now similarly, if you find A31, you will be getting plus 2, A32 you will be getting 0, A33 you will be getting minus 2. So therefore matrix of cofactors will be given by 0 minus 1 1 0 1 1 2 0 minus 2, right? So this is matrix of cofactors. Now therefore adjoint of A is transpose of this matrix. So it becomes 0 0 2 minus 1 1 0 1 1 minus 2. Now for finding out inverse, right, to find out inverse you also need to know the determinant of A. So determinant of 1 minus 1 1 1 1 1 1 0 0, right? So you'll be getting this as 0. Here we'll be having plus, here we'll be having minus, here we'll be having plus. So 1, this multiplied by this, right? 0 into 1 is 0, 0 minus 0 is 0, 0 multiplied by anything is 0. Now minus, this minus I have taken into consideration, minus 1 into, I'll be getting 1 into 1 is 1, 0 into 1 is 0, so it is 1 minus 0, plus this 1 into 1 into 1 is 1 minus 1 into 0 is 0, so it is 0. Minus into minus will be plus, 1 into 1 is 1 plus 1, so it is 2. So therefore A inverse can be written as 1 by 2 0 0 2 minus 1 1 0 1 1 minus 2, right? So this is the value of A inverse. substituting this in equation 7, we get, okay, if you substitute this particular A inverse in equation 7, we get alpha is equal to u1 u2 u3, alpha is equal to u1 u2 u3 1 by 2 into 0 0 2 minus 1 1 0 1 1 minus 2. Right, so this you can take it as equation number 8. Right, now this equation number 8, substitute equation 8 in equation 2. So we'll be getting u will be equal to 1 by 2 1 zeta square, so it is 0 0 2 minus 1 1 0 1 1 minus 2, and here you will be getting u1 u2 u3. Right, so now proceeding further, what I'll be getting here is u is equal to 1 by 2 as it is, so it is 1 into 0 is 0, zeta into minus 1 is minus zeta plus zeta square. Second element will be 1 into 0 is 0, zeta into 1 is zeta plus zeta square. Third element will be 2 into 1 is 2, zeta into 0 is 0, minus 2 zeta square, u1 u2 u3. Right, so that is how you multiply it. Fine. So further simplifying, we'll be getting u is equal to, I'll take this inside, so it is minus zeta plus zeta square divided by 2, zeta plus zeta square divided by 2, 2 is common over here, so it becomes 1 minus zeta square, so it is u1 u2 and u3. Right, so this equation I'll take it as equation number 9. Also we know that, so in the shape function class, that is in the previous video, I have shown you that u is equal to n1 u1 plus n2 u2 plus n3 u3 for a quadratic element. Now expressing above equation in matrix form, we get, so we need to check out what we'll be getting. U is equal to n1 n2 n3 u1 u2 and u3. So this I'll take it as equation number 10. Now comparing equations 9 and 10, we get, right, comparing equations 9 and 10, we get, so these are the two equations which you need to compare. Now on the left hand side both are u, on the right hand side u1 u2 u3 u1 u2 u3, so there are these two things what we need to compare. so which directly says that n1 is equal to minus zeta plus zeta square divided by 2, n2 is equal to zeta plus zeta square divided by 2, and n3 is equal to 1 minus zeta square. Right? These are value of shape functions in terms of natural coordinates. Now let me check out the variation part. So variation of n1, n2 and n3, how exactly these things are going to vary, right? So to find it out, let us consider the same element. So I'll draw an element here. Once again I'll draw an element here, and also I'll draw an element here, because I need to show three shape functions, right? So I have taken three elements of equal length. Let us say each is having three nodes. At the center we are having one more node, at the center we are having one more node, at the center we are having one more node. So if you want to show the variation of the first shape function, which is n1, yesterday we have studied that the value of the shape function at its own node is unity, whereas for all other nodes it is 0. So if you want to show n1, so value of n1 at node number 1, this is my node 1, this is node 2 and node 3. Same thing, node 1, node 2 and node 3. Node 1, node 2 and node 3. So value of shape function for n1 at node number 1 is 1, and for all other terms it is 0, right? So how you are going to show it? I need to draw a curve like this, right? So this is how you are going to show the variation, and this curve is n1. In the previous derivation, where we have considered a linear element, an element with two nodes, there you have drawn this as a straight line because it was linear. Now you need to draw it as a curve because this is quadratic. For 3, n1 is 0, and for node 2 the value of n1 is 0, right? Now similarly, variation of the second shape function. For second shape function, you will be having n2 is equal to 1 at node number 2, whereas n2 value at 3 and 1 will be 0. So here also you are going to show it like this. So this is n2. Be careful, this is not a straight line, this is a curve because it is quadratic variation. And at last we are showing shape function 3. So I need to show that the value of shape function at this particular point is +1, and at here and here it is 0. So I need to show it like this, right? So this is n3, right? So this is n1, this is n2, and this is n3. So that is how you are going to show the shape function variations, right? Fine. So that is the end of the derivation. Now before you could wind up with the today's session, I need to discuss one more important thing relating to your FEM, which you will be using in all the bars, beams, trusses, heat transfer, anything, any concept you take up, there we'll be studying stiffness matrix. So we need to know what are the properties of stiffness matrix. Okay, very important from your exam point of view, it may be from your competitive exam point of view, important for understanding the concept further. Properties of stiffness matrix, right? So first I'll write the properties, then I'll explain what it means. So first one, it is a square and symmetric matrix. Second one, sum of numerical values of row and column will be 0. Right? Sum of numerical values of a row and column will be 0. Third one, the determinant of the matrix will always be 0. Fourth one, the principal diagonal elements will always be positive. That is the fourth characteristic. Now, fifth one, size of stiffness matrix. Size of stiffness matrix is equal to the number of degrees of freedom, at times you call it as DOF, of the element or system. Right? DOF of the element or system. So I have noted down 5 important properties. Now I'll just go on explaining. Let us take an example. Let us take an element which is having 3 nodes, say 1, 2 and 3. Say there is some force which is, okay, let us consider an element which is having 3 nodes. So this is node number 1, node number 2 and node number 3, and there is some force acting at the third node. And because of this force, what is happening here in this direction, we are having a displacement in x direction. Here also we are having displacement in x direction, displacement in x direction. So each of the nodes are going to be displaced in x direction. So in this particular case, what I can say here is the total degrees of freedom is 1, 2 and 3. Right? So degrees of freedom is 1, 2 and 3. So this is 1, 2 and 3. The number of independent directions in which the movement can take place because of this force, that is degrees of freedom. Now 1, 2 and 3. So the size of the stiffness matrix in this case will be 3 into 3. I repeat, because there are 3 degrees of freedom, size of the stiffness matrix will be of the order 3 into 3. Right? If the degrees of freedom are 2 in some other example, then the size of the stiffness matrix will be 2 into 2. That is what is the meaning of the fifth characteristic or fifth point. Now I have just taken an example of a stiffness matrix 4, -4, 0, -4, 0, 8, -4, -4 and 4. Right? So I have just taken up an example of a stiffness matrix now, which explains all the points which I have written over here. Now here I'll take it as U1, U2, U3, U1, U2, U3. So these are the displacements what I have written. Right? I have considered a 3 into 3 matrix for example, and these are the degrees of freedom or the associated nodes 1, 2, 3, 1, 2, 3. That is how you are going to write it. Now what is our first property? It is a square and symmetric matrix. Right? Fine. It is a square matrix because the number of rows is equal to number of columns, so it justifies that it is a square matrix. Now second one, he says that it is a symmetric matrix. So what do you mean by symmetric matrix? Symmetric matrix is nothing but so the thing what I have marked, these are the principal diagonal elements. Now you just check out the elements above the principal diagonal and below the principal diagonal, that is -4 and -4, 0 and 0, -4 and -4, right? So if these elements remain same, then we call it as symmetric matrix. So you take up any stiffness matrix hereafter in any of the example, it may be beam, bar, truss, heat transfer, you'll find the same kind of matrices. So that is the meaning of symmetric matrix. So the elements on each other side of the principal diagonal will be same, right? So I am done with fifth point, I am done with first point. Next I'll go for the second point. Sum of numerical values of rows and columns will be 0. Now you just check it out. So here it is 4 minus 4, you'll be getting 0. Then you are having -4 -4 -8 and +8, you'll be getting 0. 4 and -4 will be getting 0. So all the rows are 0. Now let me check out with the column. So 4 and -4 is 0. -4 and -4 is -8. There is also +8, so it becomes 0. 4 and -4 once again it is 0. So you can just check out all the sum of all the rows as well as columns is equal to 0. So here it is 0 0 0. So that is what is the meaning of the second one. Sum of numerical values of row and column will be 0. So that is also a property of the stiffness matrix. Third one is the determinant of the matrix will always be 0. So we just find the determinant of this 3 into 3 matrix, you will be getting it as 0, and that is once again the important property of stiffness matrix. And the fourth one is the principal diagonal elements will always be positive. Now here you can just check out the thing which I have marked in red color, 4, 8 and 4. These are called as principal diagonal elements and these are positive, right? It is not only in this example, you take up any example hereafter and you take up the stiffness matrix, you will find all these 5 properties will be holding good, will be applicable to all the stiffness matrices what you study hereafter, right? So I hope things are clear. Thank you. Please do subscribe my channel, share this with your friends. That's it we have for today's session. Have a good day.